This is the third and final video on astronomy and cosmology in the 9702 A-level physics syllabus. It's a new topic that has been added, and I've produced two videos, part 1 and part 2 videos, and this is the final part 3 video, which focuses on cosmology, that is Hubble's law and the Big Bang theory. Now the objectives are as follows. You should understand that the lines in the emission spectra from distant objects show an increase in wavelength from their known values. Use delta lambda over lambda is approximately equal to delta F over F, approximately equal to V over C for the redshift of electromagnetic radiation from a source moving relative to an observer. Explain why redshift leads to the idea that the universe is expanding, and recall and use Hubble's law, that is V is approximately equal to H naught D, and to explain how this leads to the Big Bang theory. So you're just required to use SI units here. Right, in my part 1 video I looked at standard candles. In my part 2 video, I looked at stellar red-eye, and here I aim to look at these objectives. Please make sure to subscribe to the Physics Tips for Cambridge Students YouTube channel. Hit the bell notification so that you get alerted of future videos, and like, share, as well as to comment. Without much further ado, let's get started. Right, so we've just gone through these objectives, so we are going to move straight to where we're supposed to be. All right, cosmology. Right, so we start off with the Big Bang theory as a model of the evolution of the universe from an extremely hot and dense state, approximately 13.8 million years ago. The theory is also responsible for the birth of the space-time fabric, which has been expanding ever since. After the Big Bang, fundamental particles such as quarks and forces such as gravitation came into existence. Subsequent expansion led to cooling and formation of atoms, stars, and galaxies. One question that cosmologists cannot answer is why the Big Bang happened in the first place. There are so many theories which they have suggested, but unfortunately they are not tested. Now, evidence of the Big Bang using spectra and Doppler effect. A study of spectra from diffraction grating on telescopes used by astronomers shows that the galaxies are moving away from us. The more distant a galaxy is, the faster it moves further away. Now, in the AS syllabus, we studied the Doppler effect of sound waves. So this is when the observed wavelength of sound for a receding source, that's a source that's moving away, is longer than that of a stationary source, and it is shorter for an approaching source. Please revise that topic if you do not recall it anymore. The same happens with EM waves. So Doppler effect also takes place in EM waves. A receding source, that is the source that is moving away from you, a source that is emitting EM waves, that is, tends to have longer wavelengths. Now, if you look at longer wavelengths, you're talking of the red in the electromagnetic spectrum. Right, let me just write here. So we have Roy GBV, right? So increase in wavelength will be in that direction, and increase in frequency is in that direction there. Okay, so the frequency increases from red to violet, and then the wavelength increases from violet to red. Now, an increase in the wavelength is called redshift. So blue shift refers to an increase in the frequency or a decrease in the wavelength. So we're going to call that. So they normally focus on the blue rather than the violet. So we've got red and blue. So red shift, it means that we have longer wavelengths. That is for a receding source. A source that is moving away tends to have longer wavelengths. So observed wavelengths of all spectral lines from distant galaxies are longer than the ones observed in a laboratory using our diffraction grating. So this is known as the redshift, like I said. So this is an illustration that shows that if the observer stands there and then observes a source of light that is moving to the left, the wavelengths begin to be longer and then shorter towards this other observer on the other side. So blue shift to this observer, but red shift to the other observer. Now, if you take, for instance, the sun, right? You've got the sun there, and then it is emitting all wavelengths, right, of light. We've got light coming from the sun, and then here happens to be a cool gas. So, for instance, what I'm modeling here is we have got stars. So the stars emit radiation. Radiation passes through this space between us and the Earth. So say this is our Earth over there, and then we put our telescopes there so that we view that, the diffraction grating. Now, the gases that are in between, we've got hydrogen, we've got helium, and so forth. So this cool gas is going to absorb only those wavelengths that are characteristic to it, right? Such that when you observe these, so let's say you put this grating over there. So on the grating, diffraction grating, you are going to observe dark lines over there. So which means these have been absorbed by the cool gas. So it's called an absorption spectrum. So an absorption spectrum, dark lines on a bright background. Again, this was covered in spectral lines. Then the emission spectrum would be bright lines. So when this gas that is absorbed these colors, it's going to de-excite. Okay, so excitation during when it absorbs these energies that are characteristic to it, and then when it de-excites, it's going to emit those wavelengths that are characteristic to it. So according to here, we are seeing these bright lines on a dark background. So the background is going to be dark now, and then we have these bright lines. So this is the emission or a bright line spectrum, emission spectrum. So the spectrum that comes from the sun is a continuous spectrum, but then if there are gases in between, they're going to absorb those wavelengths that are characteristic to it or to themselves. So we're going to get dark lines for the absorption spectrum and bright lines for an emission spectrum. So this is an absorption spectrum when you see these dark lines. Right, so as you can see, red shifting of the absorption spectral lines can be observed this way. So suppose we do have this in the lab using our diffraction grating. So this source, we can just say this is the stationary source that is not moving. And then if you observe now light that is coming from distant galaxies, you find that these wavelengths are shifted. They are shifted towards the red spectrum. In other words, shifted to the right. So we are going to call this a red shift. So to find the red shift, it's going to be delta lambda there, or delta F, that is responsible for that. So that will be the same there. That will be a delta lambda for the wavelength, delta F for the frequency. Remember, C is equal to F lambda. So when lambda goes up, frequency goes down, and when frequency goes up, lambda goes down, because the speed of light in the vacuum is the same, which is 3 times 10 to the power of 8 meters per second. So this shift is called the redshift. So absorption lines in the spectrum of galaxies are all shifted to longer wavelengths, that is redshifted. The top spectrum is the spectrum of the stationary source of the sun. We are going to say stationary inverted commas. Why? Because we know the sun moves. But this is what we observe in the laboratory. But then from distant galaxies, this is what we get. Now, this leads us to Hubble's law, which states that the recession speed, that is the speed of moving away of a galaxy, is directly proportional to the distance d from us. So v is proportional to d, where the constant of proportionality is called the Hubble's constant, h naught. The SI unit for the Hubble's constant is per second, which is second to the power of -1. And the experimental value of h naught is found to be 2.4 times 10 to the power of -18 per second. Right, so remember, this is the d, distance from us. This is the d that we were finding in the part 1 video when we were finding the radiant flux intensity, where we said it's equal to L over 4 pi d squared, where d is the distance from us. So this d is the same as that d that we are finding here in the Hubble's. So we can use Hubble's law to verify the distance of a galaxy from the Earth. Now the graph below here shows the relationship between the recession speed v and the distance d of the galaxies. So this is the speed, and then this is the distance. Right, so as you can see, there is a scatter of points which just represents the uncertainties in the observations when the experiment was done. But they all lead to the fact that there is the direct proportionality between v and d, since our graph is passing through the origin, like there. Right, so as you can see that for galaxies that are moving with high speeds, right, galaxies that are far from us, so this is the distance from us here. Now when you look at galaxies at this distance here, their speed is relatively small compared to the speed of galaxies that are very far away. We are talking of 1 point something times 10 to the power of 24 meters away from us. So these galaxies are moving faster away from us. So the recession speed increases for those galaxies that are already far away from us. So distant galaxies have higher recession speeds as compared to the galaxies that are nearby. Now the gradient of this graph here is called the Hubble's constant, which is h naught. The scatter of the data shows considerable uncertainties in the observation. I've alluded to that. Now I'm going to use to work out example number 6 here, just to reinforce Hubble's law. A galaxy is at a distance of 9.5 times 10 to the power of 24 meters from us, and is moving away with a speed of 2.1 times 10 to the power of 7 meters per second. Calculate the Hubble constant based on this data. Now the Hubble constant comes from the fact that v is equal to h naught d. So h naught is the Hubble's constant. So making it the subject there is going to be v over d. Now v we have been given is 2.1 times 10 to the power of 7 meters per second. and D has been given is 9.5 times 10 to the power of 24 meters. And if you do that, you find the Hubble constant to be 2.2 times 10 to the power of minus 18 seconds. Then part B says estimate the speed in kilometers per second of a galaxy at the distance of 1.9 times 10 to the power of 25 meters. Now, the distance is doubled, that is from 9.5 times 10 to the power of 24 meters to 1.9 times 10 to the power of 25 meters. Since V is directly proportional to D, therefore V also will be doubled. So it's going to be 2 times the 2.1 times 10 to the power of 7, which gives you 4.1 times 10 to the power of 7 meters per second. So we're just going to use simple proportion there. Then we are going to talk about the Doppler redshift again. So in this time, or like on this time, we're going to be going back to our spectral lines that we had there, where we had our delta lambda, or I say delta lambda for the wavelength, and it's going to be delta f for the frequency as well. Okay, so this is the redshift. So the term refers to the increase in the wavelength due to the movement of the galaxies away from us. All the spectral lines show an increase in the wavelength, is shown on the diagram of the spectral lines that I've shown you. So the fractional increase in the wavelength depends on the recession speed, v of the galaxy. Right? So for non-relativistic galaxies, those moving with speeds far less than the speed of light in vacuum C, we can use the relationship delta lambda over lambda is equal to delta f over f, which is equal to v over c, to find the speed with which they are moving. Okay. So lambda here is the wavelength of the EM waves from the source, that is from the galaxy, and delta lambda is the change in the wavelength. F is the frequency of the electromagnetic waves from the source, and delta F is the change in the frequency. V is the recession speed of the source, and C is the speed of light in a vacuum. Now, astronomers and cosmologists assign a value for the term redshift. For example, a galaxy that shows a redshift of 7%, it means that the change in the wavelength over the wavelength, or is approximately equal to the change in the frequency over the frequency, which also gives a ratio of V over C of 0.07, which is 7 over 100. Example number 7. The spectra drawn below show the dark absorption lines against a continuous visible spectrum. So that's the shift that we're talking about over there. So this is light from a source in the laboratory, and then this is light from a distant galaxy. Now this time our red is over there and our blue is over there. So we can say that this is our delta lambda or delta F. Okay, so that's the same thing there, which is that. So that will be our delta F or delta lambda over there. A particle line in the spectrum of light from a source in the laboratory has a frequency of 4.570 times 10 to the power 14. The same line in the spectrum of light from a distant galaxy has a frequency of 4.547 times 10 to the power of 14. This was supposed to be 4.574. Sorry about that. Or 4.547. That's fine. The frequency decreases. Yeah, yes. When the lambda increases, frequency decreases. What speed is the distant galaxy moving in relation to the Earth? Is it moving towards or away from the Earth? So the first thing to do is to write down the known quantities. So the emitted frequency is 4.570 times 10 to the power 14. That is from the stationary source. And then the new frequency from the distant galaxy is 4.547. So we find the shift in the wavelength delta F. It's going to be 2.3 minus 2.3 times 10 to the power of 12 hertz. The speed of light is 3 times 10 to the power of 8. Then applying our Doppler redshift equation, delta F over F is equal to V over C. So delta F over F, so 2.3 times 10 to the power of 12 over the frequency 4.547 times 10 to the power of 14 is E times the speed of light will equal V. Right? So which is going to give you 1.5 times 10 to the power of 6 meters per second. Now the question says, is it moving towards or away from the Earth? Now the fact that the frequency has decreased, it means that the lambda has increased. So it has redshifted. So which means it is receding or moving away from Earth at that particular speed, 1.5 times 10 to the power of 6. Then we've got this example here again. The tadpole galaxy has a recession speed of 9,400 kilometers per second. Calculate the fractional change in the wavelength of the observed spectrum. So the speed in meters per second, remember we're told to use SI units, so we change that to meters per second, so it becomes 9,400 times 10 to the power of 3 over the speed of light in a vacuum. So V over C will be equal to the fractional change in the wavelength. So that gives you 0.0313. So this, since we have been given to 2SF, we should leave it as 0.031. Then practical activity, evidence of the Big Bang theory using a balloon. The expansion of the universe can be compared to dots on an inflating balloon. As the balloon is inflated, the dots all move away from each other. So if you make dots on a balloon and then start blowing it, the dots start to move away from each other. In the same way as the rubber stretches when the balloon is inflated, space itself is stretching out between the galaxies. That is with time. So just like the dots, the galaxies move away from each other. However, the galaxies themselves do not move. Then lastly, we are going to look at estimating the age of the universe. Hubble's law provided the first evidence for the birth and subsequent expansion of the universe. Distant galaxies appear to be moving faster. However, since light has a finite speed, looking deeper into space means we are looking further into the past. The further back in time we go, the faster the galaxies are receding from each other. This is similar to playing a movie in reverse, thus going to the beginning of the universe. Data from Hubble's law can be extrapolated back to the point that the universe started expanding, i.e., the beginning of the universe. Therefore, the age of the universe, T naught, is equal to T naught, which is equal to 1 over H naught. The age of the universe can be estimated from Hubble constant, that is in the example below. So a galaxy is found to be moving away with a speed of 2.1 times 10 to the power of 7 meters per second. The galaxy is at a distance of 9.5 times 10 to the power of 24 from the Earth. Assuming the speed has remained constant, what is the age of the universe in years? So applying Hubble's law, V is equal to H naught D. We rearrange it to find H naught, which is going to be 2.2 times 10 to the power of minus 18 per second, according to this data. Then after we do that, we then use T naught is equal to 1 over H naught to get the time at the beginning, which is going to be 4.52 times 10 to the power of 17 seconds. If you convert this one into years, it's going to give you 1.43 times 10 to the power of 10 years, which is 14.3 billion years. In conclusion, there are many experimental evidences that support the Big Bang theory, one of these being the temperature of the universe itself, the expansion of the universe, and subsequently the redshift. These evidences suggest that everything around us, including us, was created during the Big Bang, ultimately suggesting that we all have the same age. However, the cause for the acceleration of the galaxies remains an unknown, which is called dark energy. Now, this is a summary of definitions in astronomy and cosmology that you could look at. Now, in my part 1 video, I talked about the type 1a supernovae, which I said it is as a result of its white dwarf when it implodes or explodes at the end of its life. So these stars, when they've burned up all their hydrogen used in as nuclear fuel, the fusion in the star's core produces heat and outward pressure, but this pressure is kept in balance by the inward push of gravity generated by a star's mass. So this is not in your syllabus, but it's part of the formation of a type 1a supernova. So a lot of information was shared here. Please go through the video slowly and write comments where necessary. Remember to subscribe to the channel Physics Tips for Cambridge Students, and like as well. Signing out.